Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at the concepts of total probability and Bayes' theorem. These are concepts that are interrelated. We'll do total probability first, and we'll use total probability to later derive Bayes' theorem. Before we get too deep into this, we first need to reconsider the notion of a partition. So take a look at the figure that's on the screen right now. Events A1 all the way up through A9. Here's A1, A2, A3, all the way up to A9. Events A1 through Events A1 through A9 partition the sample space S. That means events A1 through A9 are mutually exclusive, and collectively they exhaust the sample space S, meaning that A1 union A2 union all the way up to A9, that all equals the sample space. They collectively exhaust the sample space S, and AI intersect AK equals the empty set where I is not equal to K. All right? The events A1 through A9 have no overlapping elements, and they collectively exhaust the sample space S. B, for purposes of the discussion that we're about to have, is any other event. I've shown it here just as a blue circle. It could be any event, any event. So B is any other event. All right. So let's write down some true statements, referring back to the previous figure. Event B can be written as B intersect the sample space. Any event equals itself where it intersects the sample space. I can rewrite this as B intersect the exhaustive union of A1 and A2, A3, all the way up to A9. All right? This is because of the notion of a partition. Events A1 through A9 partition my sample space. All right? By using the distributive property, I then have, let's make this B intersect A1 union B intersect A2 union and by the way, in the figure that I showed earlier, I used 9 events to partition my sample space S. I could have any number. All right. Now notice that, let's go back over here. A1, well, A1 doesn't intersect S in this particular figure, but A2 intersects B there. A7 intersects B here, etc., etc., etc. All of these events are non-overlapping. They are all mutually exclusive. B, where B intersects each of the partitioning events A1 through A9, those intersecting sets are mutually exclusive. So I can apply the third axiom and get this. the probability of B is going to be the probability of B intersect A1 plus probability B intersect A2, etc., etc., etc. This is by application of the third axiom. Third axiom of probability. Third axiom of probability tells me that the probability of the union of mutually exclusive events is the summation of the probabilities of each of those events. All right. Recall then from conditional probability the following statement. Probability of B intersect A sub I equals the probability of B if A sub I times the probability of A sub I. It's just a statement of conditional probability. All right. So now what I'm going to do is take my statement of conditional probability and plug it back. I'm going to take this statement, plug it into this relationship here, and I get the following relationship. The probability of B equals the summation from I equals 1 to M. Probability of B intersect A sub I. That is also written as summation from I equals 1 to M. Probability of B if A sub I times the probability of A sub I. That relationship there is known as the theorem of total probability. All right. The probability of event B is equal to the summation of the conditional probabilities of B some partition times the probability of A sub I. Add them all up. M can be any number. In my earlier example, M would have been 9. In this figure back here, M equals 9 because I had 9 partitioning events in my sample space S. In general, M can be any integer. M is the number of partitioning events in sample space S. Okay. Let's do an example. What I've got is I've got 2 boxes, and we're going to assume that these 2 boxes are closed to start with. Box 1, and we're going to assume it has 8 nickels and 2 quarters. Box 2 will have 20 quarters and 5 nickels. All right. We're going to assume that these boxes are initially closed. And identical. All right. My chance experiment is then going to be a two-stage experiment. One, pick a box at random. Pick a box at random. And then 2, close your eyes, open the box, and pick a coin. I guess we might have to assume that you've got gloves on so you can't tell the difference between a nickel and a quarter. We want you to randomly select a coin. So close your eyes, open the box, and select a coin at random. I'll say at random. All right. And the question is, what is the probability that I select a quarter? Probability that I selected a quarter after this 2-stage experiment. Okay? You'll notice that this is a two-step experiment. All right? Okay, let's do the math. I'm going to let B1 equal the event that I select box 1, and B2 equal the event that I select. All right? B1 and B2 will partition the pick a box sample space. You either pick box 1 or you pick box 2. You cannot pick both of them. They are mutually exclusive and they collectively exhaust the pick a box sample space. I'm using B a little bit differently than I used in the figure earlier. B1 is now defining a specific event which partitions the pick a box sample space. Likewise for capital B sub 2. All right, well, the probability of picking box 1 will equal the probability of picking box 2, and we'll say that's a half because the boxes were identical and there's no reason for you to choose one box over the other. The probability that I then pick a quarter, if I choose box 1, is 2 chances out of 10, or 1/5. And the probability that I pick a quarter, given that I picked box 2, is 20 chances out of 25, or 4/5. So using total probability, the total probability of my selecting a quarter after this 2-stage experiment is probability that I select a quarter given that I selected box 1 times the probability of selecting box 1 plus the probability that I select a quarter if I picked box 2 times the probability of picking box 2. And so this is going to be 1/5 times 1/2 plus 4/5 times 1/2, and that equals 5/10, or 1/2, 50%. All right, so compare this to the expected results if I only had one box and all of the coins were intermingled. All right. If I only had one box and all of the coins were intermingled, then the probability of randomly selecting a quarter would have been 22 chances out of the 35 total coins. There are 22 quarters total in the two boxes out of 35 total coins, and this works out to be 62.8%, 0.628. And that's certainly not equal to a half. All right? All right. So not only did we see a relatively simple application of the concept of total probability here, but I also want you to take away from this experiment that how you perform the experiment affects, dictates in fact, the likelihood of expected outcomes. All right? How you perform an experiment. How you perform an experiment determines and affects the probability of various outcomes occurring. It affects the likelihood how you perform an experiment affects the probability of the various outcomes. All right. Let's do another example. All right. So you've got some numbered chips in a bag. And you're going to, these chips are numbered 1 through 10. We've got a bag of chips numbered 1 through 10. All right? And I'm going to pick two numbers without replacement. So my chance experiment is pick two numbered chips at random, and I'm going to define some events here. A sub I equals the event that we picked the ith chip on the first draw. Let's call that on the first selection. And I, of course, is going to be an element of the set of integers 1, 2, 3, all the way up to 10. And I'm going to let event B equal the event that we picked the chip with 5 on it on the second draw. All right. B is that we reach in the bag and pull out the chip that has 5 on it on the second draw. What I want to know is, what is the probability of B? What's the probability? What's the probability that I pull a 5 out of the bag on the second draw? All right. So let's put this together. The probability of selecting chip I is 1/10 on the first draw for all I. It's 1/10 likely that you'll pull out any given chip on the first draw, no matter what the chip number might happen to be. All right. I'm going to need a little bit more room, so let me go to a fresh page. Same example. The probability that I choose a 5 on the second draw, given that I was not 5, given that I is not 5 on the first draw, is 1/9. The probability that I reach into the bag and grab the chip with a 5 on it, given that the first chip I pull out does not have a 5 on it, that probability is 1/9 because there are 9 chips left over and one of them had a 5. The probability that I pull a 5 on the second draw, given that I pulled a 5 on the first draw, is exactly 0. All right? The probability that I pull a 5 on the second draw equals 0 if I pull a 5 on the first draw. All right. So, what's the total probability of pulling a 5 on the second draw? Probability of pulling out a chip with a 5 on it on the second draw is a summation from 1 to 10. Probability of B given A sub I times the probability of A sub I. And this is going to be 9 times 1/9 times 1/10, which is 0.1 or 1/10. All right. This summation, the things we add up in this summation are identical to one another 9 times out of 10. And the one time that it's different, the probability of drawing the chip numbered 5 on the second draw, if the chip was 5 on the first draw, that one's 0. That's why we only add this up 9 times. Alrighty? All right. So let's move on then to Bayes' theorem. Bayes' theorem is an extension. Well, it's not an extension. Bayes' theorem will use total probability, as we'll see right now. All right, let's write down a couple of true things. Right now, I'm going to do some, I call it mathematical gymnastics. I'm going to write down some true steps, perform some mathematically correct analysis, and come to a result that at first won't make a lot of sense. Bayes' theorem at first glance is not going to make a lot of sense to you. It's something that you gain some facility with after doing lots of examples. So we're going to spend some time doing lots of examples with Bayes' theorem. Right now, just hang tight with me. let's do some mathematically correct steps, do some mathematical gymnastics, and get to a true result. All right. First of all, true statement. Probability of B intersect A sub I equals probability of B if A sub I times the probability of A sub I. That's just conditional probability. All right. Likewise, probability of A sub I intersecting B is probability of A sub I if B times probability of B. This is also just simply a statement of conditional probability. All right? But by the commutative property, probability of B intersect A sub I equals probability of A sub I intersect B. Just simply a true statement. Probability of the intersection is the probability of the intersection. So that allows me to use, or to equate rather, the right-hand side of the first two equations. So I can write this down. Probability of B if A sub I times the probability of A sub I equals the probability of A sub I if B times the probability of B. All right. From total probability, I say this. Probability of B equals, from total probability, probability of B is I equals 1 to M. Probability of B if A sub I times the probability of A sub I. And from my relationship here, I can rearrange and get probability of B if A sub I times probability of A sub I divided by probability of A sub I if B. All right. So this statement here. This statement here is a statement of total probability. This statement here comes from rearranging that relationship. One more rearrangement, and I get the following. Probability of A sub I if B equals probability of B if A sub I times probability of A sub I divided by summation I equals 1 to M probability of B if A sub I times probability of A sub I. This relationship is Bayes' theorem. Relationship is known as Bayes' theorem. All right. Let's write Bayes' theorem down one more time. Probability of A sub I if B equals probability of B if A sub I times the probability of A sub I divided by the summation that's Bayes' theorem. This is also known as the a posteriori probability. A posteriori probability. And the reason this is called a posteriori probability is because it applies after a chance experiment is performed. And you'll also notice that, you'll hear me say this from time to time, that it involves a switching of the question from the data we have access to. And again, this is something that'll come out in the examples that I do. It involves a switch the question type problems. So, for example, you'll notice that on the left-hand side I have A sub I is the primary event, and over here it's the conditional event. On the left-hand side, B is the conditional event, and it's the primary event over there. All right? Again, this is not at all obvious what Bayes' theorem might mean. It's best examined by a series of examples. We're going to do lots of examples starting right now. The partitioning events A sub I through A sub M and the other event B are just like we saw in the figure at the beginning of this video lecture. All right. This is always a fun example. So there's a professor who gives a test. Professor gives a test. And over the years, this professor's been teaching this course. Perhaps it's ECE-340. This professor's been teaching this course for many years. And as students come into the testing room, the professor asks a simple question, and the answer is either yes or no. The professor says, "Did you study for the test?" T is the event that student studies for the test. And this is self-reported data. I'm not asking you how much you studied, or I'm not asking you about the quality of your study time. I'm simply saying, did you study, yes or no? And over time, 70% of this professor's students have said that they've studied. Probability that students have reported that they've studied is 0.7. 70%. 70% of this professor's students have reported to the professor that they have studied. All right? You'll notice that studying or not studying partition the did you study sample space. Studying T and not T, event T and event not T partition the did you study sample space. All right. All right. The professor has given lots of tests in this particular course. He's made observations over time. He's graded lots of papers, and he's been able to determine that the probability that a student passes the test given that they study equals 90%. All right, so this is the event that the student passes. All right, this is the student fails. All right, and the professor has also been able to observe that the probability that a student passes given that they did not study is only 5%. All right? And this is all based on past data. This up here and this is all based on past data. That's all based on past data. All right? So, professor then has the next semester's worth of students. He gives a test, and a student comes up to him after the class and says, Dr. Duncan, perhaps I really studied hard, and yet I failed the test. So, what the professor wants to ask is, after the next test, what I want to know is, what is the probability that a student studied given that they failed the test? What's the probability that the student studied given that they failed the exam? All right. Well, recall this. This is one of the relationships we derived when we first started talking about axiomatic probability. Go back a couple of lectures and you'll find this one. Likewise, similarly, the probability of A naught if B equals 1 minus probability of A if B. And this is without proof. It's a true statement. I'm not going to prove it. Okay? It follows directly from this derived probability relationship earlier. All right, so let's do the math then. The probability that little Johnny studied, given that he failed the test, is probability that he failed, given that he studied, times the probability that he studied, divided by my statement of total probability. That's a frowning face. All right. Now I'm going to employ this relationship. This is just by straight application of Bayes' theorem. Now I'm going to apply this relationship to simplify and do my calculations. This can be rewritten as 1 minus probability of passing, given that student studied, times probability that the student studied, divided by 1 minus probability student passes given that they study times probability that they study plus and you'll recall earlier the probability that the student studied was 0.7, therefore the probability the student does not study is 0.3. Alright, we have access to probability over here. We have access to the probability values that we need. The probability that a student passes the test given that they study, and the probability a student passes the test given that they do not study. Plug all of that into this relationship at the bottom of the page and do the calculations, and we get 0.197. That's about 20%. All right. So, based on past observations that the professor has made, students have walked into the class and he's asked, did you study, did you not study? 70% of the times the students self-reported that they studied. Professors graded the tests and determined the likelihood of passing given that they've studied and given that they have not studied. A student takes a new test into the future and comes to the office and says, I really studied, but I failed the test. Professor says to himself, what is the probability that this student really did study given that they failed the test? Looks like in this case it's 20%. All right, making predictions into the future based on past observations and data that was collected. All right, let's do one more example. All right. I've got an assembly line that makes parts of some sort, and we're going to test these parts for defects. Parts off of an assembly line are tested for defects. The parts should fail and that will be event F if a defect is present. If the part is defective, that's event D. If the part fails the test, that's event F. All right, parts should not fail. They should not fail if not defective. All right, but I can make errors. I've got two types of errors that I can make. The first error is a part with no defect fails the test. It's possible for a part with no defect to fail the test. No test is perfect. This is called a type 1 error. a non-defective part fails the test. The second type of error is that a defective part might pass the test. This is known as a type 2 error. All right. All right. So for this particular test, we've been doing it for a long time. Based on prior observations, we've collected a lot of data. We know the following. Based on past observations, we know that the probability that the parts are good, probability that they are not defective, is 95%. We also know this. We know the probability that a part will fail, given that it's not defective, is 3%. This is a type 1 error. And we furthermore know that the probability that a part will fail, given that it is defective, is 98%. All right. I can rearrange my last bit of data this way. The probability that let's just leave that for a little bit later on. Okay? All right, so I want to find two things for this particular example. I want to find the following. I want to find the probability that the part is defective if it fails the test. I'm going to find the probability if the part is defective if it fails the test, and find the probability that it is not defective given that it does not fail the test. I want to find those two probabilities. All right. Probability that it's defective if it fails the test using Bayes' theorem is probability that it fails given that it's defective times the probability that it's defective divided by probability that it fails if it's defective times the probability it's defective plus probability that it fails given that it's not defective times the probability that it's not defective. All right. Probability that it's not defective, probability that it is defective probability that it is defective equals 1 minus the probability that it's not defective, and that's 5%. All right, it's 5% likely that my parts are defective. So, plug in data that I already know from the previous slide. This is 0.98 times 0.05 divided by 0.98 times 0.05 plus 0.03 times 0.95. That works out to be 0.632, or 63.2%. So let's talk about that for a second. What this is saying is that 63.2% of my 63.2% of the time, my part is going to be defective if it fails the test. 63.2% of the time, my part's going to be defective if it fails the test, which means around 37% of the time, the part was just fine. I think we would like to drive this closer to 1. We want that to be closer to 100%. We'd like to know that if the part fails, it failed because it was indeed defective. We would like for this percentage to be as close to 100% as possible. You'll notice that for this particular calculation, that's my type 1 error. All right? I claim to you that for this particular example, this is a textbook example, and textbook examples are, they pick the number so that the results work out nicely. I claim to you that this type 1 error for this particular problem is large. I claim to you that that type 1 error is quite large. Why is that? Well, notice as the type 1 error gets smaller and smaller and smaller and smaller and smaller. If the type 1 error gets smaller and smaller and smaller, that portion will go towards 0. It'll get smaller and smaller and smaller. And this ratio here that's left over will approach 1. All right? Ideally, I want my parts to fail if I do the test and they're defective. I want the probability that a part is defective if it fails the test to be as close to 1 as possible. I do that by fiddling with my testing procedure so as to reduce my type 1 errors. If I can drive my type 1 errors down, then I can drive this probability here closer and closer and closer to 1. All right. Let's do the other piece to this example. I want to find the probability that the part is not defective, given that it doesn't fail the test. So from Bayes' theorem, I just get this probability that it doesn't fail if it's not defective times the probability that it's not defective. Probability not defective, probability that doesn't fail, given that it's not defective, times the probability of not defective, plus probability that it doesn't fail if it's defective, times the probability that it's defective. Plug this in, and I get 1 minus 0.03 times 95%. Do this math, and I get 0.999 or 99.9%. That looks pretty good. The probability that it does not, the probability that it's not defective, given that it passes the test, is 99.9%. The probability that is a non-defective part, if it passes the test, is 99.9%. So if I happen to test a part, it doesn't fail, it's 99.9% likely that if I sell this part to a customer, it was a good part. Conversely, probability that it has a defect, if it doesn't fail, is 1 minus probability that it's a good part, and that is 0.001. Probability it's defective if it passes the test is 1%. So it's only, a tenth of a percent. It's only a tenth of a percent likely that it's a truly defective part if it passes the test. That's good news for your customers. All right. One final thing. I want to look at total test error. The probability that the part fails, given that it's non-defective, I stated earlier, was 0.03. This is type 1. That's type 1 error. The other type of error is the probability that it does not fail the test. It passes the test, given that the part is truly defective. This is 1 minus probability that it fails the test. If it is defective, that is 1 minus 0.98. That is 0.02. This is my type 2 error. All right, my type 2 error is 2%. My type 1 error is 3%. So my total test error So when you're doing a test and you determine your type 1 and type 2 errors, you add them together to get the total likelihood of making an error when that test is performed. So the total test error is 5% in this particular case. All right? Well, that's all for today. That serves as my introduction to Bayes' theorem and total probability. As always, if you have any questions, please feel free to contact me at your earliest convenience. Have a nice day. Bye-bye.